Hey everyone, welcome to Code Harmony. Today we are going to solve LeetCode problem ID 2685. Count the number of complete components. This problem is based out of graph theory, and here we will be utilizing very good graph theory concept, which is disjoint set union. Let's try to understand the problem statement first. Here we are given an integer n. There is an undirected graph with n vertices. Vertices are from 0 to n minus 1, and along with that we are also given edges array, where edge is I, every item. We have an undirected edge from A to B. If let's say the edges array is something like 0 to 1, it means there is one edge from 0 to 1 and vice versa from 1 to 0 as well. Now this is given to us a number of vertices in the graph and number of like all the edges from the graph. Then return the complete number of complete connected components in the graph. Return the number of complete connected components in the graph. And yeah, this question has been asked in Amazon 3 times in the last 6 months. Amazon is frequently asking questions on disjoint set union, so it's a very good problem if you are preparing for Amazon. Here if we try to understand the input again, what is given to us? What is given is number of vertices. Number of vertices, if n is equal to 6, the vertices are from 0 to 5, and these are the edges. Vertex 0 is connected to vertex 1 and vertex 1 is connected to vertex 0. These 4 bidirectional edges are given to us. Now given part is over, and what is our operation? Operation is find the number of complete connected components. Complete connected components. We are aware of this problem. Find the number of connected components in the graph. What does that mean? Let's firstly ignore this complete part. Find the number of connected component in the graph. Now let's understand this example. Here in this example, number of vertices are given as 6. So we have vertices from 0 to 6, 0, 1, 2, 3, 4, 5, excluding 6. From 0 to 5, this is 6 in number. And edges are these are the edges from vertex U to V and the vice versa as well. If I just try to draw this graph by utilizing the edges, if I just don't use any of the edges, how many connected components are there? 1, 2, 3, 4, 5, 6. 6 in number. There are 6 connected components. Every single vertex itself is a connected component. And if I utilize the first edge will become like this. Here the connected components goes from 6 to 5. 1, 2, 3, 4, 5. If I just show you 1, 2, 3, 4, this is the 5th connected component. Now the connected components are 5. If I utilize this edge, 1, 2, 3, 4. Connected components are 4 in number. If I use this edge, 1 to 2. 1, 2, 3, 4. Connected components are again 4. If I use this edge, 3 and 4, 0, 1, 2. Sorry, 1, 2, 3. Connected components are 3 in number. We have used all the edges, and now the connected components are 3. But in the problem, they are not asking us to find the number of connected components. So here, from these components, this graph, the connected components are 3 in number. But they are requiring us to figure out the complete connected component. And what does a complete connected component mean? It is written in the problem statement. A connected component is a subgraph where there exists a path between any two vertices, and no two vertex subgraph share an edge with a vertex outside of the subgraph. Okay, this is a connected component definition where like every two vertices are connected directly or indirectly, but it will become complete if there exists an edge between every pair of its vertices, every two pair. If from any of the connected component, let's say if I just pick this one, 0, 1, 2. If you pick any two vertices, if I pick 0 and 1, yes, there is an edge. If I pick 1 and 0, yes, there is an edge. If I pick 0 and 2, yes, there is an edge. But if it was something like this, 0 connected to 1 connected to 2, here every two component is connected directly or indirectly, but we want directly connected. 0 and 1 is connected directly, yes. 0, 2 is connected directly, yes. 1 and 2, this is not directly connected, it is connected via 0. So this is a connected component, but this is complete connected component, and what we have to return is number of complete connected component. So now I will just directly give you that idea. So in the connected component, first of all, how do we figure out the number of connected components? For that, there is a very good algorithm or data structure which is called disjoint set union. Disjoint set union, or you can somehow like find the name like union find algorithm. On this concept, I have prepared a dedicated video, and you just go and watch this video, and this will be really helpful for you, because solving question doesn't matter, you should know the concept in great detail. So just cover up this concept if you are not very confident about it, otherwise just move ahead with the solution. Now, how do we figure out the number of connected components? Here, this is the example given to us. If I example was already copied. What we do in this case, let me show you the disjoint set union approach. What we do is we create a parent array of same size as the number of vertices. I call it parent 1 2 3 1 2 3 4 5 6 0 1 2 3 4 5. Every element is parent of itself. Now if I just connect 0 and 1, let me mark the items as well. 0, there is no edge initially. 0 1 2 3 4 5. Combine 0 and 1. I will just figure out the parent of 0 and parent of 1. Parent of 0 is 0 itself because it is -1, and parent of 1 is 1 because it is -1. So parent of 0 is 0, parent of 1 is 1. Just combine these two parents as well. In this case, we are connecting two components, so these two will be connected, and whatever is the one you can choose as a parent. Let's say I have chosen 0 as a parent, so 1 will have a 0 as a parent and 0 will have -1. The next edge is 0 and 2. If I connect 0 and 2, so here parent of 0 is 0 and parent of 2 is 2. So parent of 2 will become 0 now. 1 to 2. Parent of 1 is 0, parent of 2 is 0. There is no need to do anything because these two are already connected. 3 and 4. Parent of 3 is 3, parent of 4 is 3. So parent of 4 will also be 3 now. Parent of 5 is -1. So this is the parent array, the final state. Zero is the parent, 1 has a parent 0, 2 parent is 0, 3 is a parent of itself, 4 has a parent of 3, 3 is the parent of 4, and 5 itself is a parent. So here this is my parent array. Whatever is the -1 is the parent of their respective connected component. So here by just checking the count of -1, we can get to know that how many parents or how many connected components are there. There are 3 connected components, but here we might require the size of the connected component. See, like in what case the connected component will be the complete connected component. There is one thing that I noticed in the constraint, that there are no repeated edges. All the edges are perfectly fine. So it means you can consider that the input is valid. So if a connected component is complete, in that case every two vertices are connected to each other. It means how many number of edges we should have in that connected component. how many edges? Every vertex should be connected to every other vertex. If I just pick one vertex, what are the different possibilities we are left with? N minus 1. Now we are trying to figure out that whether in what scenario the connected component will be the complete connected component. In that case, first of all, we should know that every 2 element from that connected component is having an edge between it. What is the see, first of all, let's see what is the probability, what are the ways we can pick 2 elements in this connected component, right? So there are, let's say, 3 in number in this connected component. The size of this connected component is 3. If I have to pick 2 elements, it will be something like this: 3 into 3 minus 1. Probability to pick first element is n, the second element is n minus 1, n into n minus 1. So these are the pairs in which we can choose the element. For the first element we have 3 possibility. For the second element we have 2 possibility in this case. But here we are not worrying about the permutations. We require the combination. How many different pairs are there? For the pairs, just divide it by 2. Why? Because we have considered 0 to 1 as well and 1 to 0 as well, and both of these are same, and every edge we are considering twice. So total number of edges we need to figure out. Edge count, in short, we have to figure out edge count of every component. Edge count of every component. How many edges are there in this component? N into n minus 1. But the edges given to us are unidirectional. Unidirectional means index vertex A to B, vertex AB. If this is a bidirectional edge, it is given to us only once. And if my component is having 3 nodes, the total number of edges should be n into n minus 1 divided by 2 for that component. And the total number of edges given to us that we can already figure out from the given input. So what idea I'm trying to tell you is, first of all, you should be checking what are all the connected components. If you have all the connected components, along with that, just try to capture the size of that component. Size of component. So let's say somehow you have captured the size of the component as well. How can we check the size of component? Whenever we are merging 2 components, let's say component with parent 0, component with parent 1, whatever is the size of this, size will be combined to the parent, whatever parent you are going to choose. So what you have to do is, you have to figure out the parent array, prepare the parent array to give me all the connected components. Along with that, size of every component you have to capture. Now the size of every component, let's say the size of the component is this. So how many edges do we require? We require size into size minus 1 divided by 2. Size into size minus 1 divided by 2. Size into size minus 1 is the number of pairs we can have, number of permutations we can have for any 2 elements, and divided by 2 is the number of edges related to that parent. Let's say the parent is P for this connected component. So P should have these many edges given in the starting input. Let me show you how. So here one connected component was something like this: 0 1 2, 0 1 0 2 1 2, and this formed this component. And in this component the parent is 0 and the size is 3. So what I will do is, I will go through every edge, and every edge is going to be from u to v. It means u is a vertex, v is a vertex, u will be the part of any component. So I first for the first edge I will check 0 is a part of this component, and the size of this component is 3, correct? So this component 0 has a edge count is 1, edge count will be increased by 1. So what I will do is, let's say parent or vertex, you just add a map edge count. Parent 0 has a edge count of 1. In this case 0 has a parent of 0, so 0 will be updated to 2. 1 has a parent which is 0, which was 0 in the initial stage. 1 also has a parent is equal to 0. So 1, there is one more edge, so edge count will be increased to 3. So there are 3 edges, and 3 4 the parent was 3 and the edge count was 1. So this edge count we are going to utilize 3 is the edge count. Edge count is equal to size of this component. Size of this component was 3 into 3 minus 1 divided by 2. So yeah, this is same. If this is same, it means that we have got our answer. It means the connected component have all the required number of edges, and every edge is a unique, every edge is fine. So yeah, this approach we are going to use. So for that, what we require so far is one disjoint set union, one union find class, UF class, and in the UF class we have to maintain the parent array. Along with the parent array, I will be maintaining the size of that connected component. And for every edge is from u to v. For every parent of u, count the number of edges, how many edges are there, and for that we will just going to put the formula for every parent. For every parent, what I'm going to do is size into size minus 1 divided by 2 should be equal to the edge count. So this formula we have to use, and then we'll be able to get the answer. So it's based out of mainly disjoint set union, and let's have a look on the code. In case you are getting some doubts, you can just ask in the comment section below. Here in the code, first of all, I have created a union find class where we have two major functions, find the parent and union, two connected components. And when we are doing the union, we also need to carry the size, and the size initially is 1, because in the starting every node itself is a connected component. So initially the size is 1, parent is initialized with -1, and find array with the path compression, and union these two connected components. If they are already part of same component, then do nothing. Otherwise, whatever is the parent of bigger block, just remain him the parent. Okay, once the union find algorithm is done, just do the union of every single edge. Apart from that, edges count is required, because ultimately this is the equation we are going to use. The size of every component, let's say the size of component is size, the total number of pairs we can form, total number of permutations we can form is n into n minus 1, n into n minus 1, and this is the permutation. We want the edges, because edges are already bidirectional, edges are divided by 2. Now permutation to combination, we have done it. So these are the number of items, number of edges we require for every connected component. If we have enough edges, it means that connected component is a complete connected component. So union find initialization to the union, map find the edges count, whatever is edges is going from u to v, and whatever is the parent of u, just add one edge into that entry. And then for every parent we have to check the answer, for every component we have to check the answer. Yeah, this is the equation, and yeah, this is my answer, and this code is going to be working fine. I hope you understood the code. At least you have understood the approach. Just do let me know in case you are not able to understand it, and feel free to discuss in the Discord community attached to the description below. Thank you guys, bye bye.